Okay, now we are recording. So let's start. So thank you everybody for being here, and thank you Professor Glenn Webb for giving this for accepting to give this last seminar in the seminar series of COVID-19. So actually, it is a great honor to have you, Glenn, between us today. So let me say a few words about Professor Webb. So actually, I'm going more or less very briefly summarize a very nice volume on dedication of the work have done Professor Webb has done, which is entitled Glenn Webb, A Career in Mathematics, which was published in 2008. Professor Webb has authored or co-authored over 140 papers, written various research monographs, and co-edited 4 volumes. He has given plenary lectures, colloquia, and seminars across the globe, and he has served on the editorial boards of at least 11 archival journals. He has been the dissertation advisor of 16 students, or even maybe now more. Glenn was born in Cleveland, Ohio, but he grew up in Miami, Florida. He attended Georgia Institute of Technology with the original intention of studying chemical engineering. However, he quickly turned to mathematics. So thank you for that, Glenn. and he has a very stellar career. In particular, Glenn, along with Michael Crandall, Amon Pacey, Emin Brace, Bob Dorough, Toshio Kato, Reggie Jerry Goldstein, and Bob Martin, was one of the pioneers in the area of nonlinear accretive operator theory and nonlinear semigroups and evolution operators, which has a lot of impact in various areas of research, apart of course mathematics. In 1974, he got a prestigious research fellowship to visit and to study in Italy, particularly in Rome. He fell in love with Rome and in Italy, and he had a very active career over there. He has a fantastic line of research, particularly in epidemiology, and that's the reason we invited him today to give this seminar. So Glenn, thank you very much for giving this seminar, and today Glenn is going to talk about, as you can see, a model of COVID-19 epidemics predicting the impact of vaccination in the US. So Glenn, the floor is yours. Please take it away. Thank you.
Thank you very much for the kind introduction and the invitation to present this seminar. I thank everyone for being here this afternoon. I will say that I have been to Mexico many times, to Mexico City quite a few times, but also Oaxaca and other places. I always enjoy my visits to Mexico, and I have many Mexican friends, so it's great to be here this afternoon. I want to talk about COVID-19 epidemics and mathematical models that involve vaccination and the use of these models in predicting the future course of the epidemics, and in particular in the United States. So that's the main objective. And of course, we all know that COVID-19 has been such a burden on the whole world, on all of humanity, and it's caused great sadness in our lives and loss in our lives. But now there's a great hope for vaccination, that it will curtail the pandemics across the globe and hopefully eliminate the pandemics ultimately. But there's, of course, many issues involved in vaccination and how it impacts and contributes to the curtailment of COVID-19 pandemics. So there's many issues that I want to address. And a key issue is the data. The data for COVID-19. There's extensive data. In the US, it's supplied by the Centers for Disease Control. We call it the CDC. And it's very extensive. It's very up to date, but it has certain difficulties because it consists of daily reported cases. And the daily reported cases, the data is extremely erratic. It bounces up and down like a basketball. And so it's difficult to use the data in that form. So a typical way to manage this data is to take a rolling weekly averaging. So you take each week and take the average for the past 7 days, and you continue that day by day. And we call that the rolling weekly averaging of the daily reported values. And this smooths the data quite a bit, but it's still somewhat lumpy and bouncy. So that is one of the difficulties in managing the data, informing the model with the data that's available. And of course, it's different in every country across the globe. And so the transmission parameter is one of the key ingredients in any epidemic model. And the transmission parameters in COVID-19 models are extremely difficult to manage. And the reason is that they're very much time dependent. We have our traditional epidemics models, the SIR models and so on, and we set the parameters and we take off and we go forward. And so that SIR model is extremely valuable and it has been used for decades, but it assumes that there's a constant transmission parameter, and that's very, very different from COVID-19 because the transmission parameter is very much varying with time. So in my presentation here, I will try to identify the transmission parameter, that's the so-called parameter identification problem, and I will try to identify the transmission parameter in terms of the rolling weekly average daily reported cases. And so I will tell you how this is done. But before I start that, there's another significant issue, especially when we incorporate vaccination, and that is that vaccination, people are vaccinated who are susceptible and have not yet been infected, but many people are vaccinated who have already been infected. So people who have already been infected and are vaccinated are not removed from the susceptible class because they've already been removed, because COVID-19 has significant immunity to reinfection, and that's been recently confirmed. Here's a paper that you can check in Nature that shows that reinfection is very unlikely to COVID infected. And another key issue is the number of reported cases is only a fraction of the total number of cases. So in the US, the CDC has estimated that 1 in 4.3 infections were reported and 1 in 3.9 symptomatic illnesses were reported. So that's a key factor that we have to incorporate, because only 1 in 4 in the US, only 1 in 4 cases are reported. And so we will have to bring that factor into our consideration of the model. Okay, here are the compartments of the model. S of T consists of the susceptible population at time T. T will be time units in days. I of T will be the asymptomatic infectious population at time T. So COVID-19 has a very difficult feature in that infectious people can be asymptomatic. And this, by the way, was true 100 years ago. There was something called the swine flu throughout the world, which was far worse than COVID-19, by the way. In the US, it killed more than 500,000 people, and that was 100 years ago, 1919, when the US population was much less than half of what it is now. And worldwide, it's estimated that perhaps 40, 80, some huge number of people died as a result of that influenza pandemic. And that pandemic had a asymptomatic infectious period as well, but it just consisted of a few days. But that was a major factor in the severity of that epidemic. So I of T will represent the asymptomatic infectious population. R of T will represent the reported symptomatic infectious population, and U of T will be the unreported symptomatic infectious population, but U of T will be in ratio 4:1 with R of T. So U of T will just be 4 times R of T. Okay, the parameters of the model. That's always a very important feature of any epidemic model. And so in this model that I'll present, we will assume a transmission rate, which I'll label tau of T. And ultimately, it will depend on the S of T population, the I of T population, the R of T population. So that's a key parameter, as I said, and it's time varying. And so we want to identify that parameter as very important in predicting the future of a COVID-19 epidemic. Now we will assume that infectious individuals who are asymptomatic, that's the class capital I of T, are infectious for an average period of 1 over new days, where new is 1 over 7. So they'll be infectious for an average period of 7 days, 1 week. And we'll assume that reported symptomatic infected individuals will be infected also for an average period of 1 week, infectious for 1 week. And so these values are consistent with what the CDC has revealed in their data, but there's controversy about this. How long does someone remain infectious with a COVID-19 infection? It's not absolutely certain, but we'll take the period of asymptomatic infectiousness to be 1 week and symptomatic infectiousness to be 1 week as well, for both reported and unreported symptomatic infected individuals. And as I just mentioned, we'll assume that a fraction of asymptomatic infectious individuals become reported, and and the F value there will be 0.25, 1 over 4, and that the remaining fraction of unreported symptomatic infectious individuals will be the fraction F at 0.75. So there's a 3-to-1 ratio between reported symptomatic infectious and unreported symptomatic infectious. So as I said, these values are consistent with what the CDC has revealed. So here's the model. Here are the equations of the model. The susceptible individuals become infected at a rate equal to minus tau. This is the transmission rate here, which depends on these variables, S of T, I of T, and R of T. And so there's a loss of susceptibles to infection due to this transmission term, but there's again a loss of susceptibles due to vaccination. And that will be represented by this term. V of T will be the rate of vaccination per day of susceptible individuals. It has a minus sign in front of it to indicate that it's a loss term in the S equation. And the asymptomatic infectious individuals become infected at plus this rate here. Take this term with the minus sign, put a plus sign in front here. And then they transfer to the reported symptomatic infectious compartment or the unreported symptomatic infectious compartment at rates nu1 and nu2. And so these are the equations of the model, and we can ignore the fourth equation. It comes down to these 3 equations because we have assumed that U of T is in ratio 3-to-1 to R of T. So here are the 3 equations with the parameters: the transmission parameter, time dependent, the vaccination rate, lowercase v of T, and these periods of asymptomatic infectiousness and symptomatic infectiousness, each is 1 week. So that's our model. Here's the flow diagram of the model. Susceptibles can become infected at this rate, tau of T SIR, and they enter the asymptomatic infectious class, I of T. They stay there on average 1 week. Then they go either to the symptomatic reported infectious compartment or the symptomatic unreported infectious compartment, R of T and U of T. Or they can be removed from the susceptible compartment by becoming vaccinated at a rate V of t, S of t. So this is the model. And the problem, of course, is to identify the parameters, in particular the transmission parameter, the transmission rate. So what data do we have? We have daily reported cases data. And as I mentioned, it's very erratic. So we first use the rolling weekly average daily reported cases data to smooth that out, but it's still somewhat bouncy. But we use that as our source of data, and we call it the daily reported time-dependent, we call it the daily reported cases data, the rolling weekly average daily reported cases data. Now that data is discrete, it's day by day, but we can go to the model, which it has continuous time, and we can design a function capital D R of t, which is the continuum daily reported cases in the model. And it will correspond to the rolling weekly average daily reported cases data. So this capital D R of t is in the model, and it satisfies the following equation in the model with continuous time. So its derivative, the derivative of the daily reported cases in the model is equal to the entry into the asymptomatic infectious class. Remember how you got into the, where's the equation? How you got into this reported cases class in the model. You entered at this rate nu1 I of t, and then you stayed a week and you left, but you entered at the rate nu1 I of t. Nu1 was 0.25 over 7. Let's see, where was I? And so that's the entry into the daily reported cases in the model. And you exit after 1 day. So I put the 1 in front of the dr of t to emphasize that we divide this by 1 over day. So you stay in this class 1 day, you enter at this rate, you stay 1 day, and you exit at this rate. So you take this equation and you solve it for I of t. And I of t then is equal to this term, dr prime of t plus dr of t over nu1. So this is the formula for I of t in the model in terms of the daily reported cases in the model. So the equation 2 for I of t in the model had this form, remember. This is the equation for I prime of t in the model. So we solve for the transmission rate, this term right here, in the model equation, equation 2, and we get that the transmission rate is equal to I prime of t plus nu times I of t. So we have the transmission rate in terms of I prime of t and nu I of t. Remember, nu is 1 over 7. Okay, so then we take I prime of t from this formula and we differentiate it to get I prime of t, and we get this term right here. We get dr double prime of t plus dr prime of t over nu1. Then we add plus nu times I of t. So we take this term right here and we place it here. So this gives us the transmission rate in the model in terms of the daily reported cases rate in the model. And so we need to know the daily reported cases rate in the model, and we need to know the first derivative of it and the second derivative of it. So we go to the discrete daily reported cases, the discrete rolling weekly average data. We know that, and we construct a continuum cubic spline interpolation of that data. That data is discrete, it's day by day. But we take that data and we fit it with an interpolation, which is a continuum cubic spline. So this is numerical analysis. And what you do is you take the discrete data, which you have, and you take 2 intervals of that data. You go from T0 to T1 to T2. And on those 2 discrete intervals, you construct a cubic function that agrees with the data at those 3 values, but a cubic function that is differentiable, and in fact, 3 times differentiable. It's a cubic function across that interval, and it agrees with the data across those intervals. And then you intervals two at a time, you pair off and you construct cubic splines on each of the pairs, but you get the shared mesh points to match at the values and the derivatives and the second derivatives and the third derivatives. So you construct a cubic spline continuum interpolation of this discrete data in that way. And so that we call the CS of t. It's a function which has 3 continuous derivatives, and it agrees with the data at the days, the discrete days, but it's a cubic spline interpolation of that data. And so we can take the first derivative of it and the second derivative of it, and we get a formula for the transmission rate in terms of this cubic spline interpolation of the dr of t, which was the model reported cases daily obtained from the rolling weekly average data discrete. So that's a complicated story, but that's how we obtain the transmission rate in the model. It goes back to the reported cases, the rolling weekly average reported cases daily, and it uses the form of the model equations. Okay, so here's some information about COVID-19 in the US. And so the data will start on March 7th. The rolling weekly average will start on March 7th. The data itself starts on March 1st, but the first week gives us the rolling weekly average over the first week, which we start on March 7th. It goes out to May 1st. Now this is dated because of course we have data out to today, which is June 21st. Now I have upgraded this model to June 15th, 2021, but I don't quite have it ready to present to an audience. It's all finished, but I have it available to May 1st, the data from the CDC to May 1st. And it's not a simple matter to continue it from May 1st to June 15th, because every day the CDC back changes all the data right back to March 1st. So all the data has to be redone as you move forward. But the ideas are the same as for June 15th, which I will have available soon. I can provide a copy if you're interested. Okay, so what does this graph show? It shows the weekly rolling average daily reported cases. Those are the red dots. So if you look carefully, you see a bunch of red dots. You see the red dots, everyone? And when they're not changing very much, it looks like a solid line, but these are actually red dots throughout. Here you see the red dots, and here you see the red dots. That's the daily, weekly, rolling average reported cases data, day by day. And the green graph is the continuum spline interpolation of that data, of the red dots. It goes exactly through those red dots, but it has this feature that it is 3 times continuously differentiable. And the vertical bars are the daily reported cases. So you see the vertical bars are bouncing around tremendously, and that's very difficult to use that data. It's impossible to use that data. It's too ragged. So we use the weekly rolling average of that. Those are the red dots, and then we interpolate that with the curve CS of t. So that's the data story. Now here's the continuum transmission from March 1st, 2020 to May 1st, 2021. So you see that transmission function is time dependent. It's obtained from the CS function, and it's bouncing around tremendously. It has a tremendous bounce right here, for example, at about January 3rd. But that's the transmission. It is highly variable in time, but that comes from the data. And so That's the data. We have to live with it. And the transmission is definitely a continuous, but a very bouncy function of time. Okay. Now, we want to understand the transmission rate after the last day of daily reported cases. Here it is up to the last day of daily reported cases, which was May 1st, remember. I've got it to June 15th, but not quite ready to show you. But to May 1st, it looks like this. What does it look like after the last day of daily reported cases, May 1st? Let's set T sub D to be the last day of daily reported cases. That's May 1st, 2021. And then we set a second time, we call it T1 to be May 15th, 2 weeks later. And between May 1st and May 15th, between TD and T1, there's a change in the social distancing behavior of people in the US. And approximately May 15, there was an increase in social distancing behavior because at time, before that time, there were school closings, there were shop closings, event closings. There was a very serious social distancing restriction placed on the population. But starting May 15th, there was a relaxation and there was an increase to normalcy between TD, May 1st and May 15th. And so that increase to normalcy between those two dates is represented by a new transmission term, which has this form. So this is the earlier transmission form out to the last day of daily reported cases, which was TD, May 1st. But that's multiplied times this mass action form. If you set that value T equal to TD, you get that this ratio here is 1. And if T is equal to TD, then T1 is equal to the time, sorry. When T is equal to TD, then this T is equal to TD, and that represents the time from T1 to time T2. So if T is equal to T1, this term is 0, and that matches TD, T1 is TD, so that matches the earlier transmission value. So this new transmission term is continuous at T1, and it goes out to T2, where it has this form. And we assume that after time T2, which I take to be October 1st, 2021, that's next fall, middle next fall, there's no further change in the social distancing behavior. And so in that case, when you set that T equal to T2, then this matches the earlier value for the transmission term. It matches this value when T is equal to T2. Okay, so we set the new transmission term equal to these formulas where there's an increase in social distancing behavior. And they involve a scaling factor, which I call omega, and later I'll set that scaling factor to different values to increase the return to normalcy of social distancing. So we know that in the US, social distancing is returning to normalcy, and that's occurring at these two time intervals. And so that's because there's a relaxation of the social distancing restrictions. Shops are reopening, restaurants are reopening, schools are reopening. There's sporting events are reopening. In fact, right now, as I'm talking, there's a sporting event called the CWS that's occurring. And a year ago, it was canceled. But this year it's occurring. Does anyone know what that sporting event is, the CWS? Anyone know?
No, I haven't. Sorry. I have no idea. What is that? CWS?
CWS. What is CWS?
No idea.
Anyone know? No?
No idea.
Well, it's the College World Series.
Oh,
and you know what that is?
It has to do with a competition between different universities or something like that.
That's right. It's the finals competition in baseball of universities. It's occurring right now. It began at the same time this talk began, at 5 p.m. And guess who's playing right now? Vanderbilt. Vanderbilt. They're playing for the championship. And as I told you, well, the game will go on for hours. But as I told you, the series was canceled last year, 2020. They canceled it because of COVID. But 2 years ago in 2019, guess who won? Anyone guess? Vanderbilt won. Vanderbilt won. So they're playing again. They're going to try to win. And they played the first game in the series on Saturday night, and they won. But the game went on. If you know baseball, you know that the typical game lasts 9 innings, but they can go overtime. It lasted 12 innings, but they won. Anyway, they're playing right now. We can all check it out after this talk. So anyway, that's the story on return to normalcy in social distancing, which is ongoing in the US and ongoing everywhere across the world, pretty much, with vaccination, because of vaccination. Okay, so what is the rate of vaccination? Let's take a look at that. In the US, vaccination began on December 14th, 2020, about 7 months ago. And there were 2 vaccines, Pfizer and Moderna. And of course, you need 2 doses, as you know. And from January 15th of 2021, 6 months ago, approximately 1 million people per day have been vaccinated. So by May 1st, approximately 110 million people have been vaccinated. And we call it fully vaccinated with 2 doses. The 2 doses are separated typically by 3 weeks. And now, June 15th, approximately, that's 45 more days, approximately 145 million people or somewhat more have been vaccinated. But remember, I'm calling the last day of my data here, May 1st. So going forward from that last day, we've had a vaccination rate. We know the vaccination before that day, May 1st, because we have the data for vaccination day by day. And so we want to understand the vaccination rate after May 1st, where it's been approximately 1 million people per day. And so we said, remember in my S equation, I vaccinate susceptibles and they're removed from the susceptible class at the rate V of T per day times S of T. That's a standard first order loss term. Where was I? Okay, here. So what is that rate V of T? V for vaccination after May 1st? Well, I assume that the vaccination is 95% effective. And that's controversial, but that's a typical value that one sees, that if you're vaccinated, there's a 95% chance that you will not be infected by the epidemic. And so we multiply that term V, to get V of T, we multiply by 0.955 the daily rate. And the daily rate is something we know. The daily rate is from data. And we assumed that before the last day of data, it was the given values in the CDC data set. After the last day, May 1st of data, we take it to be 1 million per day. Now that's quite rough, but it's very hard to know what that daily rate bounces quite a bit for vaccination. But on average, it's approximately 1 million. It has been. It's maybe slowing now, but we'll take it to be 1 million. So we'll take forward in time. We'll take V daily of T to be 1 million per day. Now we want to take care of the fact that when we vaccinate someone who has already been infected, we don't remove them from the susceptible class. They're already removed. So account for that. We take the rate of vaccination per day to be this 0.95 times the V daily T, but times the fraction S of T over S of 0. So this represents the fraction of people still susceptible that started out susceptible, S of T over S of 0. And then when we multiply V of T by S of T, we get the fraction of S of T that are still susceptible. And so that excludes people who were previously infected from being removed from the susceptible class by vaccination. That's a very important feature that you must have in your model. You have to account for the people who were removed from the susceptible class because they were previously infected. So that's the story. And now we want to identify a ultimate percentage of the population that is vaccinated. And we'll take it to be 90%. So we suppose that ultimately 90% of the US population will be vaccinated. So that's a simplifying assumption and somewhat controversial because it could be more, it could be less. But let's assume that 90% of the US population is ultimately vaccinated. And at this rate of 1 million a day after May 1st, 2021, 90% of the US population will be fully vaccinated by November 11th. So by November 11th, we'll have 90% of the US population vaccinated, and we'll set the vaccination rate to be 0 after that day. So this is a simplifying assumption. It can be made more careful, but that's the way we'll handle this. So here's the story on vaccination remember that May 1st was the last day of daily reported cases. So this, get rid of this. That line right there is May 1st. That vertical line right there is May 1st, if you can see it. And this is the data of vaccination in the US from the start date, December 14th, 2020 to May 1st, 2021. As I told you, I have this out to June 15th, but this is the current presentation story. And that's the daily. You see it's bouncing around quite a bit. This is the cumulative. It goes same from December 14th, 2020 to May 1st, 21. And so that's the vaccination rate before, that's the vaccination data before May 1st, the last day of data. Okay. And so we take that as our model value for everything before the last day of data, May 1st. The transmission rate, the vaccination rate, and the parameters we assigned. And this is the story for the model. And we have the compartments. If you can read this, it's small, but capital S of T is the susceptible population. On March 7th, it was approximately, I think, 31 million, 310 million approximately people susceptible. And that number went down over all these months out to May 1st, the last day of data. And according to the model, on May 1st, 2021, there were about, I think, 170, I forget, 170 susceptibles still remaining on that last day of data. And so susceptibles that hadn't been infected and susceptibles that hadn't been vaccinated were still in that class. And there were about 80 million. Now CR of T is the blue graph right here. You can't see it too well, it's blue graph. And that's the cumulative reported cases. And it goes up to, I don't know what, I can't read that value, but I think it's about 30 million, approximately 30 million. And that the blue graph is the model cumulative reported cases. The red dots are the cumulative reported daily cases from data. That's the rolling weekly average daily reported cases cumulative from the data. And it matches exactly, in fact, of course, this cumulative reported cases because it was set to do that before the last day of reported cases in the model. Now U of T is the cumulative unreported cases. That's in ratio 3:1 with the cumulative reported cases. So this green graph is 3 times the blue graph and the red dots. R of T is the reported cases. That's blue, dark red, dark U is purple. Those are the reported cases and unreported cases, also in 3:1 ratio. And this red graph is the cumulative vaccinated. So we add up the people that are vaccinated, and we have approximately 130 million people vaccinated by May 1st. So that's the model and the data that the model describes. Okay, now we want to go forward from the model from the last day of reported cases, and that was May 1st, last day of, we call that T sub D, remember? And we want to go forward until November 11th. In fact, sorry, we want to go forward to January 1st, 2022. So these are the graphs of the model output with our data that we set according to the transmission rate, which we set up after the last day of reported cases, and the vaccination rate, which we set up after the last day of reported cases. Now, between April 1st and May 1st, this little wiggle here corresponds, let's see, to, let me see here. Where was this? Yeah, that little wiggle there is the model between April 1st and May 1st. So this little red bunch of dots here and the green graph is the model values between April 1st and May 1st. So extend that up a little bit and you get this piece right here. So this is bigger here because it's a shorter scale here, but this is the data. This is the model based on data before May 1st, as we indicated earlier. After May 1st, we go forward with our model in time out to January 1st, 2022. And so we have 5 different scenarios here. This is when we ultimately vaccinate 90% of the population. Whoops, sorry, that's the wrong one. Oh, sorry. It's this one. This is when we vaccinate 90% of the population with 5 different values of this scaling parameter omega. So when omega is bigger, that means that return to normal social behavior is even greater. The bigger omega is, the greater that return. And so when omega is smallest, that's when it's green, then the number of cases, this is the daily reported cases in the model after May 1st to January 21st, 2022, that number just goes down. The R of T just goes down, just decreases to a very low level by January 1st, 2022. And the level, in fact, is 373 cases. And value is 0.06. That's this red graph. Let's see here. Blue is, I have to look at this a little bit. Sorry. Let me take a look. Oh, omega 4 is green. Blue, that blue value right there is omega equal to 0.005. This red omega 0.006, purple 0.007, and orange 0.008. But the point is there's a greater return to normalcy for the higher values of omega. For the smaller values, this DRT just decreases to low values over these months. For the higher values, it will increase through the fall, but then decrease. And for example, when omega is equal to 0.007, that's the orange graph, the number of cases on January 1st, 2022 is 1,090, but it's still going down. It will continue to go down in 2022. Now, this is a similar story, but I've changed the ultimate vaccination percentage to 85%. And so that means it's difficult to know how many people will ultimately be vaccinated in the US because of the vaccine hesitancy and vaccine opposition. But if it's ultimately 85%, then these are the graphs. And of course, then each of these values here at January 1st, 2022 is higher than when omega is 90%. And these are the values when omega, when that percentage is 80%. If we only get 80% of the population vaccinated, then we stop vaccination earlier, October 9th, and then we get still higher values. But they're still going down, and they will continue to go down in 2022. 2. So that's the story of a model that predicts the future of the COVID epidemic in the US based on the daily reported cases data, actually the weekly rolling average daily reported cases. And that data is assumed known between March 7th, 2020 and May 1st, 2021. Then we project the model forward to January 1st, 2022. And for lower levels of social distancing restoration, the epidemic will decrease rapidly to very low levels by January 2022 and continue to decrease in 2022. For higher levels, it will first increase in the fall of 2021, but then decrease to relatively low levels by January 1st, 2022 and continue to subside. But that depends on many considerations that are in doubt. And one is the presence of vaccine-resistant strains, which may be more virulent and may arrive in the US. In fact, we know there are strains entering the US from other countries now that have sometimes more virulence and sometimes vaccine resistant, but this is unclear. But in absence of that consideration, the COVID-19 pandemic in the US should subside throughout the coming months into the year 2022. Now, there's many other considerations for this story. And one is to incorporate age demographics. So the CDC has age demographics. And so here are the, just like the rolling average weekly daily reported cases graph that we saw earlier for all cases, this is the same graph for age groups. So there you see there's 9 age groups here. It starts with the youngest 0 to 5, that's this bottom one, and from March 7th to May 1st, 2021. Then the next one is 6 to 13, and then it continues. And the highest here is the green one. That's 18 to 24. 18 to 24 has the most cases. And you see early on, the oldest class, 80 plus, had the most cases. But this is the age group data for reported cases over this period of time. So we can incorporate that into the model, but it's a lot of work, of course, to get all those compartments for the age groups. This is the vaccination data, which is also available, just like the age group data cases is available. The vaccination age group fully vaccinated data is available, and this is some of that data. We can also incorporate race and ethnicity demographics into the model. So the CDC has this, and these classes here, this solid class here, this kind of orangish, yellowish dark color is the Alaskan, and this is the Alaskan, I believe that's the Alaskan population, non-Hispanic. The next one, the green one here, is the Asian and Pacific Islanders, non-Hispanic. The black is this orange dotted, that's black, non-Hispanic. The green is Hispanic, that's the highest, by the way. And the white is the red dashes, non-Hispanic. So the Hispanic US population has the highest cases per 100,000 US population, but we can incorporate that into our model. And we can also incorporate geographical regions into the model. So this is an example of last week. The cases high, substantial, moderate, low. You see Tennessee had a very substantial high, in fact, the worst in the country just about number of cases. And this is the vaccination data. Again, the Northeast has the highest fraction of people vaccinated, the South the lowest, and so on. So that's the vaccination data. And this is data for the vaccinated strains. So there's new strains coming in. This is the data for several weeks ago. The B.1.1.17 is currently the dominant strain for the US. All these features can be incorporated into the model, and that of course complicates the model tremendously, but it provides more information about what happened and what will happen. As far as what's happening in Mexico, here are the confirmed cases by state in Mexico as of April 11th, 2021. And so you see the worst in these darkest areas. And so there's a variation, considerable variation by state in Mexico in the number of confirmed cases. And this is the most recent cases in Mexico, the last 15 days, going back to June 6th to yesterday, June 20th. And we have the number of deaths, that's the purple, recoveries, blue, active cases, red. And this is the number of cases day by day by day. And this is the number of deaths. So Mexico has its own data story, its own model story, and it's very important for us to try to understand this epidemic. It's a terrible tragedy for all of us, and mathematical modeling, I think, can help to understand it, how it arrived, how it progressed, and how it will behave in the future going forward. And what we learn, we can apply to future pandemics, and there will be future pandemics for sure. It could happen 10 years from now, it could happen 100 years from now, but in fact, there will be a future of influenza pandemics, and we want to know how to handle them, and mathematical modeling can help to understand that. So I thank you all, and I wish you the best. I wish you well. I hope you stay well. I'll be happy to answer any questions that anyone has.
Thank you very much, Glenn, for this actually very fantastic and very clear talk. So I have several questions, but of course, first I would ask my colleagues if you have any questions, please just directly unmute your microphone and ask Glenn. Otherwise, you can write it on the chat, and I'll happily read it. Any questions? Okay, so let me start maybe, Glenn. So you have shown the part for the presentation of today, even though you have said that you have redone the analysis of the data for up to June 15. So the data you have, the results you have shown here is you have calibrated the model up to May the 1st, okay? And then you have extrapolated in the future to see what's going to happen with the pandemic in the US. Have you checked your predictions with the current data you have to see how good is the prediction? Have you done this thing already?
Yes, it's pretty good. Of course, it hasn't been that long. Mm-hmm. It's only been 6 weeks, I guess. And also I have variability here. I have the 90% ultimately vaccinated, the 80%, 85, and the 80%, and I have my scaling parameters. I have 5 scaling parameters, but the epidemic has subsided in the US. Mm-hmm. And it's approximately, these graphs here, there's 3 of them, they're quite similar, as you see. Mm-hmm. But it starts to change. It starts to change right through here. It's starting to change. Yes. Somewhat. So that's something that needs to be balanced with this earlier prediction, to see what the new data reveals about the earlier prediction.
And yeah, of course. And in your experience, in your actually very wide experience on this, when you use these models to calibrate and then do predictions, I mean, for how long are good the predictions? Is for 6 weeks, 7 weeks? Because normally you can predict in a very short time window, and then you have to calibrate again, right?
That's right. So that's a tremendous challenge to try to get the predictions more than a few weeks ahead, or even a few months. So that again, I think it requires an input of variability in what's happening, what will happen. We can't be we can't give a perfect prediction. An illustration is the weather. The U.S. Weather Bureau predicts whether it will rain today or tomorrow, or even 4 or 5 days from now. But it doesn't really try to predict if it will rain in Nashville 1 month from now. Why not? Because it can't. It can't have an accurate prediction of rainfall anywhere. Oh, well, it depends on how variable the weather is. But in many locations, the U.S. Weather Bureau cannot predict the weather very far forward because the parameters are too sensitive. The model that they use is basically a partial differential equation model for fluid dynamics on the surface of the Earth. But the parameters, it's so sensitive to parameters that the model just can't be done. It's not possible. Maybe someday it will be possible. But I think we have a similar story for epidemic predictions. But again, it depends on the particular epidemic, how variable the parameters are. And we know with COVID-19, as we've seen, the transmission parameter is extremely variable. Yes. And so predicting ahead very far is very difficult. So it's best to try to examine different scenarios and see what they look like. But from the various scenarios, we can get a certain idea about the trend. And from what we see here, going into the year 2022, these values should go down, and go down, and go down. And we should see this epidemic subside, but not go away, not disappear.
Sure.
It appears that it's very likely to continue, perhaps at very low levels.
Yeah, I see. Actually, I love the idea you presented, which was very simple and very nice, how you can write down the force of infection as a function of the unreported cases. I think I'm going to steal it for some ideas I have. But I wanted to ask you the following. So in principle, the number of unreported cases is this fraction new one, if I recall correctly, right? Or is related to that?
Right.
Yeah. So I would assume that this number new one changes over time, right?
Yes, but it's really not known. The value new one and new two, and it goes back to this value new. Remember, new one is 0.25 over 7, and new is 1 over 7, and new 2 is 0.75 over 7. So these values, what do they really mean? How long is someone asymptomatically infectious? Is it 1 week, or is it 10 days, or is it 5 days? It's really not known, and it's variable. But it's reasonable to assume that it has an average value of a week. And again, I think we should understand that when we say asymptomatic infectiousness, we don't mean that the person is absolutely asymptomatic. Maybe they have slight symptoms at the end of 1 week or 5, 9 days, whatever. And also reported, unreported. And the reported cases are symptomatic, but maybe it starts very low symptoms at first, and then later it's more visible symptoms. But symptoms are difficult to pin down sometimes, and so a particular case, someone may suspect they're symptomatic, but they just have a throat irritation or an allergy. So these values are quite vague in a way, and quite they're guesswork, but I think they're reasonable for this story. And we do not know their exact values, and we cannot know. But you're right in saying that they could be variable. They could be changing with time. But again, it's difficult to know how they change with time, as well as how they change over the course of the pandemic with time.
Sure. Okay, thank you. I think that Philip has a question. Philip, go ahead, please.
Hi, can you hear me?
Yes, we can hear you.
Okay. A big storm here, so I'm having some internet difficulties. But thank you, Glenn, for this nice talk. And I was wondering if this framework, if these tools have the power, sort of the statistical power to detect, you mentioned vaccine escape mutations, new variants that could be resistant to vaccine-induced antibodies. And I was wondering if this has maybe the power to detect the emergence of vaccine escape variants.
Yes, that's a very good question, because there's a tremendous lack of certainty about the variant strains and how the vaccination affects those strains. And there's hope that it may be very effective against certain of those strains, and it may be less effective against other variants, but it may prevent serious illness or mortality, although it doesn't prevent the infection itself completely. So the issue of variant strains is a very important issue. And so it could be, as I said, it could be incorporated into the model, but that's hard work, of course. All these incorporations involving age classes and ethnic classes and variant strains, geographic locations, they're all important, and they're all very difficult to incorporate into the model, but it can be done. And ultimately, I think it should be done. But as far as variant strain,
But if you were to
yes,
if you were to see, for example, an increase in new infections, having 90% of the population vaccinated, might there be some sort of critical threshold beyond which you can say, I think there's a problem?
yes, I
Yeah.
think so. If you see a jump,
There's a new,
if you
yeah.
see a jump in the
Right.
number of cases, and it could indicate that the vaccination is not effective against that strain. But so that's an issue, and that I think is one feature the model can contribute. And there's also another issue concerning the vaccination. That's a booster, and it's not clear whether or not we'll need boosters.
Right.
It's quite possible.
Yeah.
And
Yep.
so that jump in the number of daily reported cases after at a certain stage could be not because of a variant strain, but because the vaccine is actually waning and losing its effectiveness, and a booster is needed. So that's another issue. Do we need booster shots? And so that's
Right. And those are intertwined issues. Yeah.
Yeah.
So again, I think the model can help to understand that. But the data, of course, is what's happening there. But if the model projects forward and that reported projection is not attained, then it could indicate the need for booster shots or perhaps another vaccine to handle the variant strain, or it could require a further shutdown of society. So all these issues are very, very difficult, very challenging, and very important for all of us.
I agree. Thank you, Philip. More questions, because I now have another one. If I can make it. So my question is the following, Glenn. I'm going to pose it as a mathematical question. Suppose that you have limited access to information, okay, due to logistical reasons, yeah, and
Okay.
for instance, you have a cost of how you are going to extract information of a given epidemic. All right.
Okay.
And you need to allocate that cost so as to make the longest possible prediction. Which information is the most important one in epidemic model to make the longest possible prediction?
That's a difficult question, because the parameter identification problem in an epidemic model is this extremely difficult question. And we have our traditional models where we set simple values to various limited number of parameters, and we get our results. And those results, they're historic and they're very valuable. They're very important. The standard SIR model that goes back 70 years or whatever is a very valuable model. It predicts something amazing about an epidemic. It predicts the reason that we are here today, because it predicts that no epidemic will come along and destroy the human race. Remember the outcome of the SIR model? The susceptible population never goes to zero. And so that means that there's always survivors. So over the course of human history, modern humans go back at least 50,000 years. There's been thousands and thousands of epidemics that have come along, and no one of them ever wiped out the entire human race. Because of that, and we know that because of the standard SIR model, there's always you know what I'm talking about, right? There's always a remaining susceptible population that never got infected. But in general, the parameter identification model problem is very difficult for a very complex model, very elaborate, complicated, complex model. This model is already quite complicated because of the transmission rate, but we toss in all these extra features, age structure, geographical location, ethnic structure, variance. It has an enormous number of parameters that we have to keep up with, and that's difficult. And how to do it is a challenge. I think it's a new challenge for all of us, for epidemic modeling, to try to understand how to handle this parameter identification problem. And as I say, for typical epidemics, the transmission parameter is changing. It's changing with time. Behavior changes, the strains may change, vaccination changes it. So we have to incorporate many considerations. And so the current models that are out there, there's quite a few. You typically involve a huge parameterization story. And sometimes it's not very well explained. I think it involves guesswork and determination of parameters that are claimed to be the best and so on. But it's a very difficult story that we have to accept for these very complicated and difficult epidemic models.
Okay, thank you. Well, colleagues, if there are no further questions, I think I don't see raised hands. So let us thank the speaker of today, Professor Glenn Webb. Glenn, thank you very much for this fantastic, very clear and very inspiring talk. It was great to have you here virtually once, at least virtually once again in Mexico City.
Okay.
To see you soon after all this thing has gone away. And for the rest of the people, now we go to summer break, and we'll come back with more seminars after summer break. And now it's time to go back and to watch baseball, and let us hope that.
Okay,
wins,
I
right?
will. I will hope for the best, and I wish you all the best. I wish you good health, and I hope you stay well, and your families all stay well. And I hope to be in Mexico and see many of you again soon.
Yeah, we wish you the same thing. Thank you very much, Glenn. Thank you very much, everybody. Bye bye.
Thank you. Goodbye, everyone.
Goodbye.
Goodbye.